Last time we talked about thrust, which was the mass flow rate and the exhaust velocity. And today we wanted to talk a little bit more in depth about the exhaust velocity because it's an important concept. The exhaust velocity, in the most simple terms, is the speed of the particles as they come out of the nozzle. So in the thrust equation, thrust is equal to the mass flow rate times the exhaust velocity. And also in the rocket equation, the exhaust velocity shows up because that totally defines what the delta V of the rocket is. And so if you write out the rocket equation in both forms, you can see the exhaust velocity. So let's talk for a second about the specific impulse. And specific impulse is the measure of the efficiency of an engine. So for rocket engines, the exhaust velocity is specific impulse times just 9.8, where 9.8 is the acceleration due to gravity. We can write it as an equation. VE is equals ISP times 9.8. The specific impulse helps define the mass flow rate for a rocket. Let's say that you have a rocket that's just sitting on the launch pad and you fire that rocket off, and all you want is that rocket to just sit there and just not move. Like it doesn't fall to the ground or it doesn't rise up. Then at that point, you have thrust pointing up and you have gravity pointing down, right? And those things are in exact balance with each other. And if you write out the equation for this, thrust equals gravity, you have mass flow rate times the exhaust velocity equals mass of the rocket times 9.8, where 9.8 is gravity. You rearrange that and you get the mass flow rate is equal to the mass of the rocket divided by specific impulse. And so it's really easy to figure out what the minimum mass flow rate is to just sort of balance there on the launch pad, given the mass of the rocket. If you increase that mass flow rate, you'll start rising up. All right, let's go through the exhaust velocity of different rocket engines. So if we look at the V2 rocket, which was the first modern rocket, the exhaust velocity was roughly 2,000 meters per second. It was pretty slow. The Saturn V rocket had an exhaust velocity which was 2,577 meters per second. But if you look at the second stage of the Saturn V, it had an exhaust velocity which was over 4,000 meters per second. So almost twice as much as the first stage. And we'll talk about why in just a minute. The Space Shuttle main engines, which was liquid hydrogen and liquid oxygen combined to make water and this exhaust velocity, it's about 4,400 meters per second. And that's a pretty good engine. 4,400 meters per second, that's pretty darn good. The Falcon 9, which is a super popular engine, has an exhaust velocity which is about 2,700 meters per second in the first stage and about 3,000 meters per second in the second stage. All right, so a rocket engine is less efficient in an atmosphere than it is in a vacuum. And the reason for that is because atmospheric pressure sort of compresses the exhaust. So the first part of the rocket burn happens in this really high atmospheric pressure region where the atmosphere is squishing the flow of the exhaust. And so it makes it very narrow. And so if you look at a rocket launch, you will see as it goes up, the plume becomes bigger and bigger. So that first stage has to go through this atmospheric restriction region. And so it's basically inherently less efficient because it has to go through all of these different parts of the atmosphere. The second stage, on the other hand, starts off in a very low pressure environment. And so you can specially design it so it works really well in a vacuum. And so second stage engines are almost always more efficient than first stage engines. Let's talk about temperature and what is temperature. Temperature is a measure of the random motion in a gas. And so when something is colder, the molecules or the atoms are moving around less. And then as it heats up, those molecules are moving faster and faster and faster. In a gas, we have both temperature and bulk motion. So if you go outside, you have both temperature, which you're feeling, and you have wind, which you're feeling also. And so those two things are distinctly different. The first is that you have random motion of the particles, right? That is temperature. And then wind is the bulk motion of those particles. And the idea of a nozzle is to turn random motion in a combustion chamber to directed motion of the exhaust. So you have high temperature in the combustion chamber. The nozzle design creates this flow that turns the random motion into bulk motion, and then you get a large exhaust velocity because of that. So you have chemistry, which is basically when you combine two things, the question is, does it release energy or does it take energy? The first type is where you put two things together and you get an explosion or you get heat released, and that's called an exothermic reaction, which means temperature is increasing. Or when you combine things, maybe nothing happens unless you add some heat and then you get a reaction. And we can think of that endothermic reaction. We could think of that as like cooking. You're adding energy to create this reaction. That obviously doesn't help for rocket science. We want exothermic reactions where we put two things together and then we get energy released. When we combine hydrogen and oxygen, we get an exact amount of energy that is released, right? And for every single chemical reaction, when you put it together, you get a certain amount of energy released. And that has to do with the properties of the atoms and molecules. You can't get more energy unless you change the things that you're adding together. There is a lot of different types of rocket fuels, like gasoline and oxygen. That's what we use in our car, and we get a certain amount of energy release for that. Kerosene and oxygen, we get a certain amount of energy. Hydrogen and oxygen, we get a certain amount of energy from that. And when we decide what type of fuel we want to use, we balance a bunch of different factors. We want to get the largest exhaust velocity that we can get. But if it's super difficult to store these compounds because they're like super caustic or they're toxic to humans or something like that, we may choose to not use that. Hydrogen is extremely hard to actually store for long periods because it has to be super cold if you want to keep it in liquid form. Or if you put it in gas form, it is so small, the molecules are so small, they tend to escape. And so it just leaks out all over the place. So it's actually quite difficult to store. So hydrogen is great as a rocket fuel, but it's hard to actually use because of the practicalness of storing it. So a lot of rocket manufacturers actually use kerosene as their rocket fuel of choice because kerosene is super easy to store. There are other techniques for heating besides just chemistry. So we've talked about putting two things together and getting heat, but you could actually heat gases in other ways, like through electricity. You can run a current through it. You could put a nuclear power plant in your engine and you could get energy. You could put solar light in there and get some energy. You could shoot lasers in there. We're going to go into these in future lessons. But the biggest issue with all of these other things is that it's really hard to get things to heat up very, very quickly. So you're mass flow limited. When you change to these new technologies, it actually limits the mass flow rate. And remember that thrust is the exhaust velocity times the mass flow rate. So if you can't have a large mass flow rate, you limit the amount of thrust, even though you've increased the exhaust velocity a bit. The other issue that we have is that we have these metals that we use to build our nozzles and our combustion chambers and everything. And if we add too much heat, we melt our components. So what we really need to do is design new components for our combustion chamber using new metals and stuff that actually have a much higher melting point. One other technique that we can do is instead of heating stuff up, we could actually just accelerate the particles by themselves. And so this is like the Large Hadron Collider, where you create like an ion, you put it into an electric field, and you accelerate it. And that technique, this creating ions, putting them in electric fields, creates really, really large exhaust velocities, like 2 to 10 times larger than chemical engines, but it's really mass flow rate limited because it's really hard to create ions on a massive scale. So it has very, very small amounts of mass. It's very hard to generate these ions. So in summary, the exhaust velocity is where a lot of the science in rocket science is located. Most engines work by turning high temperature gases into exhaust velocity. So you combine two things, it creates an explosion, very hot temperature, very random motion, and then you use a nozzle to direct that random motion into kinetic energy or into bulk flow energy. These chemical engines are really good to get us off of the Earth because you can have huge mass flow rates for them. There are a lot of other techniques which we'll go into in future lessons that can have higher temperatures or exhaust velocities, but then the mass flow rate becomes the limiter, and then it's really hard to use them in rockets to get off the ground. So chemical rockets will probably continue to be used to get into orbit, but then moving around in space once we get to orbit, we're probably going to use new techniques pretty soon. And so we look forward to that in the future. And we'll talk about those types of engines in a lot more detail in lessons to come.